Okay, so let's try to continue with the tutorial. For the first 5 minutes, I'll be checking the relevant comments and just make sure I'm able to improve on those that will be relevant. So I'll be solving a question and yet trying to pay attention to the other side so that I just check those comments that can be important. So we'll continue from question 2. Hopefully we'll be able to do question 2 and 3. Then question 1 will be redone, due to the problem that we had earlier. So I'm just asking you to, only those with relevant comments, if you really need help this session, then just post the relevant comments for the first 5 minutes. Then you will continue with whatever you do in the other part of the time. So for now, let's concentrate on improving our quality. Let's try to do this. I'm writing something on the board so that we should just make sure that you're able to see. So that is on question 2. The question says, a ball of mass M attached to a massless string of length R is being wheeled in a vertical circle as shown. Show that the minimum speed that the ball needs at the top of the circle in order for it not to leave the circle is given by root of RG. So we want to show just stop. Okay, so I think this time it's visible. Just make sure that your quality of the video, if you can't see well, you just go on 720 pixels. I think that would help. Otherwise, the zooming here has already been done. So a ball of mass M attached to a massless string of length R is being wheeled in a vertical circle as shown. Show that the minimum speed that the ball needs on top of the circle in order for it not to leave the circle is given by root of RG. So if you have a ball, we imagine this is our string, it's massless, then you are taking it in a vertical motion like that. Then the question is, we have to show that the minimum speed that is required to keep it moving in a circle is just equal to root of RG. So on top there, if my ball is here, then it's coming downwards there. So we're saying this is the string, and we know that there is centripetal acceleration, which is AC. So the question is show that the minimum speed, which you can call V min, is equal to root of GR. So now for us to handle this question, we need to consider the forces that are acting on this ball as it is going in this circular motion. So at the top of the circle there, I can draw a free body diagram. I know I will have the mass times gravity, which is the weight of the object, down there as a force. Then I also have the tension force from the string. So we have tension and mg. Then we know this thing is having a centripetal acceleration just down here. So if I have this free body diagram, this is my x-axis, this is my y-axis, then I can also make my reference. So this will be my negative down, positive up, positive here, and negative on the other side. So now we have to remember that this centripetal acceleration is just caused by what we call the centripetal force. So the summation of forces acting on this ball is the one which is producing the acceleration. So let's resolve the forces. We're saying summation of forces in the y-axis. These will produce an acceleration which is centripetal, and this is negative because we've considered our down to be negative. So the summation of forces in the y is just equal to negative ma centripetal. Then what are those forces? We know we have tension, so we have negative tension minus mg. These will produce a negative m times acceleration. So we can just multiply through by a negative to simplify this. So we multiply by a negative, we get T plus mg is equal to mac. So now we know that if you are swinging a string vertically, there will be tension in the string itself. Now when it reaches the maximum, when it reaches the top part, we know that it will have the highest tension if it has the maximum velocity, and it will have less tension. The string will have less tension if you have less velocity, implying that the smaller the velocity, the smaller the tension, and the higher the velocity, the higher the tension in the string. Now, for us to consider the minimum possible speed to get this going, then as it reaches here, the tension has to be equal to 0. So on the top here, when you're using the minimum speed, we expect this tension here to be 0, because tension in a string that is not taut is just 0 unless it's fully stretched. That's when we can have tension here. Now for the minimum speed, meaning this thing is going very slow, very close to stopping. When it reaches the highest point there, we expect the string to just lose its tension and become 0. So we're saying for Vmin, for the minimum speed, for Vmin, this will just be, for Vmin, tension is just equal to 0. So if tension is equal to 0, that implies that mg will just be equal to mac. So the m is common, we can cancel it out. Now remember, and we know that AC is just equal to V squared over R. Therefore, this G is simply equal to V squared over R, and V squared is equal to GR. Hence, the V is just equal to root of GR. Hence, we have shown. So we say hence shown. V is just equal to root of GR. And that's the end of the problem. So the only thing you need to take note is, in this scenario, if you're looking for the minimum speed, then your tension has to be 0 here on top of the circle. So if it's 0 on top of the circle, then T becomes 0 in your equation where you're resolving the forces. Therefore, mg is equal to ma, and you make, you know that A is equal to V squared over R. So you make V the subject of the formula. It's bringing you back to this, and hence shown. So we can go to part B of the question. If the ball has that speed given in part A at the top, show that the speed at the bottom will be given by root of 5 rg. So now we're coming to the bottom of the circle. So if the string now comes here and it's continuing in that motion, allow me to call the top as my point 1 and the bottom as my point 2. So with my reference, we want to find the velocity at point 2. So we are simply showing that the velocity at point 2 is equal to root of 5gr. So now to do this, let's consider, remember we know the conservation of mechanical energy. So from the conservation of mechanical energy, we know that mechanical energy at point 1 will be equal to the mechanical energy at point 2. So from the conservation of energy, we're saying mechanical energy at point 1 is equal to mechanical energy at point 2. So if this is the case, then we need to know that mechanical energy is just equal to the potential energy plus kinetic energy at point 1, then potential energy plus kinetic energy at point 2. So at point 1, so we're saying at point 1, we have kinetic energy plus potential energy at point 1, which is just now. What is the kinetic energy at point 1? We know that this is half mv squared at 1 plus mgh at point 1. Now recall from part A, from the first part we already found what V1 is. That was the minimum speed on top of the circle. So I'm saying we have to recall from part A that V1 is just equal to root of GR. We already established that. So this implies that the mechanical energy at point 1 is just equal to half m then GR, which is just the V squared there, it's GR, then plus mg. Now, what is h in this case? It's the height. So from, if this is my reference point, this is my 0 point, from here to here, we just have the diameter as our height. So if this is the diameter, then it's simply 2 multiplied by the radius r. So we have 2r. So this is the mechanical energy at point 1. Then at point 2, mechanical energy at point 2. So if we are here, we are still saying it's the kinetic energy plus potential energy at point 2. So the kinetic energy at point 2, we know it's still half mv2 squared plus the potential energy at point 2, because now our height here is 0, this will just be equal to 0. So we come back to the conservation of energy. We're saying mechanical energy at point 1 will be equal to mechanical energy at point 2. So we can equate the mechanical energy at point 2 to the mechanical energy at point 2. At point 1, I mean. So from mechanical energy at 1 is equal to me at 2, we get, I'm equating the 2 now, half mgr plus mg2r. This will just be equal to half mv2 squared. So we're actually looking for V2. So we have to make it the subject. Now we can see that m is common, so we can cancel out m. If we cancel out m, then we're remaining with half gr plus 2 gr is equal to half v2 squared. So if this is v2 squared now, we can make it the subject because the question is almost done. We just simplify it. You can multiply both sides by 2. So you multiply this by 2, then you also multiply this by 2. Then you get gr plus 4gr is equal to v2 squared. And from here now we are able to see that v2 is just equal to the root of 5gr, and hence we have shown at v2 we just have root of 5gr. That is our velocity here at the minimum point. the bottom part, because we called the velocity here as v2. We considered this part as 1 and this one as 2. So the only thing you need to remember on this part is you need to apply the conservation of mechanical energy. So when you conserve the mechanical energy, we have potential energy plus kinetic energy being equal to the potential energy plus kinetic energy at both points. And hence that question is done. So we can say hence shown. Then from here, the other question is find an expression for the tension in the string at the bottom of the circle. Find an expression for the string in this for the tension in the string at the bottom of the circle. So we are still here and we want to find the expression for the tension. So again, let's just draw a free body diagram for this situation here. So let's draw a free body diagram. At the bottom there, we know this is my x-axis, this is my y-axis. So we are going to have the mg down here. Then now, since it's at the bottom, the tension is on top. Yeah, so we have mg down and the tension on top. And the acceleration, the centripetal acceleration in this case is upwards, because it's always towards the center of the circle. So the centripetal acceleration will be directed upwards to the center of the circle. So we say summation, so this is, I make my reference, this is my negative, positive, negative, and negative there. So we have positive on the upper y-axis, negative down, positive on your right x-axis, then negative on the left. So if we are to sum up these forces from Newton's second law of motion, summation of forces in the y, these will produce the acceleration mac. So we have tension, which is positive, minus mg. This will be equal to mac. Now remember that this acceleration, we know that the acceleration is just equal to v squared over r, the radius. And we know that from our question, it's saying at the bottom, meaning this is just the v2 that we have already found on this part, which is v2 is equal to root of 5gr. So we have to come up with the expression. So we're saying therefore T is just equal to m v squared, this is 2, over r, then plus mg. So in this case, v2, we already found it. Our v2 is just equal to the root of 5gr. So if we substitute in this equation, we have T is equal to m5gr divided by r plus mg. So you can see that that will cancel out, and hence the tension is just equal to 6 mg, and that is the tension in the chord. So this is the tension in the chord, it's just 6 mg because the r and the r cancelled out. So to find the tension in the chord at the bottom, you just need to apply Newton's second law of motion. When you apply Newton's second law of motion, you have to remember that the centripetal acceleration is just equal to v squared over r. So if it is v squared over r, then we substitute in that equation, we are getting T is equal to mv squared 2 over r plus mg. Then you have to remember that v2 was already found. It's the velocity at the bottom of the circle, and that is just equal to root of 5gr. And so we can simplify the equation where the r will cancel out and we have t is equal to 6 mg. And what forces cause the acceleration? If we assume the fisher is holding the string somewhere here and he's swinging it, so we assume he's holding it like this, then swinging it downwards like that. So this hand is fixed, it's not moving. Then what is moving is the sinker down here. It's the one which is making a circular motion. So as it is moving down there, making that circular motion, we're saying this is the sketch that we have for our problem. So the sinker is going in a circle like that, and this is the center of the circle. Then the question is, what is the angle theta that this is making with the vertical? And the other question is, what is the direction of the acceleration? So we already know that the acceleration in circular motion is, for uniform circular motion, is always towards the center, which is the centripetal acceleration. So the direction of acceleration is the centripetal force. But in the same way, we understand from Newton's second law that a force produces acceleration, and it produces an acceleration in the direction of the force itself. So now, if we need to know the force that is producing the acceleration, we need to know the force that is in the direction as same as the acceleration. So how do we get to that force? We know that this sinker has the weight mg downwards there. Then in the string here we have tension. Now if I make my axis, this is my y-axis and this is my x-axis, it means this tension is not in the x or in the y, so we need to resolve it into its components. Meaning, since my theta is here, I have from here I have t sine theta in the x because my angle is here. So I have t sine theta, which is just opposite the angle. Then I have t cos theta in the y-axis. So those are my forces. I have mg, t sine theta, t cos theta. So from here I'm able to tell that the force which is in the same direction as the acceleration is just t sine theta. Hence the force responsible for the acceleration is t sine theta. My direction is towards the center of the circle and the force responsible is t sine theta. Now the question is, what is the angle theta? So for us to know what the angle theta is, let's try to resolve the forces acting on this sinker. So we go to summation of forces in the x. We know this is where the acceleration is being introduced, the centripetal acceleration. So we have t sine theta. So if my reference here is positive, negative, negative, and positive there. So my up is positive, my down is negative, then here I have positive and negative there. So t sine theta, that's the only force I have in the x-axis, is the one which is producing the acceleration, mac. So now, at this point, I think I have tension here, so I'll go to the y-axis and see what I can get rid of. So I'll call this one equation 1. Then I'll go to the y-axis. In the y-axis we have t cos theta and we have mg. So what we're going to do is, let's resolve forces in the y-axis, summation of forces in the y. This produces an acceleration centripetal, but we don't have the centripetal acceleration in the y, so we're saying, or it produces, so it's a, but acceleration in the y is equal to 0. So the acceleration in the y is 0. That implies that there is no motion in the y-axis. Therefore, t cos theta minus mg would just be equal to 0. Or t cos theta is just equal to mg. Now, at this point now, I'm seeing something common if I compare to equation 1. So what I will just do is I'll make T the subject to the formula here. I'll make T the subject to the formula there. So if I make T the subject to the formula, T will just be equal to mg divided by T cos theta. So if this is the case, T is equal to mg cos theta, so I'll call this one equation 2, and I know now I can substitute equation 2 into equation 1 so that I get rid of the T, because we don't have the value for the tension in this particular question. So let's substitute equation 2 into 1. So sub equation 2 into 1 gives mg over cos theta multiplied by sin theta. Sin theta, these will just be equal to MAC. And now we're able to identify from here that sin theta over cos theta is just tan theta. So this equation can be written as tan theta mg is just equal to MAC. So from here we are able to see that m is common, we can cancel it out, and that implies that tan theta is equal to AC over G, and therefore theta is just equal to tan inverse of AC over G. So now if we check the question, we don't have the acceleration, the centripetal given, but we know gravity is a constant. So what we're going to do is, let's try to simplify this acceleration from what we don't know and just try to take it to what we know. So how do we simplify that? So to simplify that, we're saying we know that AC is just equal to V squared over R. Again, the velocity in this case hasn't been given. Has it? So we have, from the question, what do we have?